Today I'm going to be completing part A of homework 2 for separations. And to get started here, we're going to derive the Rachford-Rice equation for vapor-liquid equilibrium, and then we're going to show that it is a monotonic function of only the vapor mole fraction. So to get started here, we know that our total moles of our feed are always going to equal our moles of vapor plus our moles of liquid. And subbing, furthermore, we know that for a component I of our feed, our Zi, our feed fraction of component I times our feed, is going to equal our Yi, vapor fraction, times our vapor, plus our Xi, times our liquid. And then if we take this and we divide out our feed, and consider that phi equals our V over our F, we get that Zi is going to equal Yi times our phi plus Xi times 1 minus our phi, as we can sub out for L over F. We know that that is going to be 1 minus V, so we can get our Xi times our 1 times 1 minus phi. Moving on from this, we're going to need to consider, we know that Ki equals Yi over Xi. We can sub this in order to find an expression for only Xi. So putting that into our equation, we get that Zi Yi equals Ki Xi. It's going to equal Ki Xi phi plus Xi minus Xi phi. And then factoring out our Xi, we can get Zi equals Xi times Ki phi plus 1 minus phi. And of course, solving for our Xi, we get an expression for our Xi based entirely on our feed component Zi divided by our Ki phi plus 1 minus phi. And we know that going into a problem, it's usually pretty trivial. We almost always know our Zi, our feed composition for a given component, and we can also pretty easily find our Ki. So knowing those two variables means that we only need to find our phi, which we can find by making an initial guess and finding the root. So if we also find an expression of this for Y, we can get, well, first of all, we know that Xi must equal Yi over Ki. And subbing this in, we get Zi equals Yi phi plus Yi over Ki times 1 minus phi. If we multiply everything by ki, we get that ki zi is going to equal yi phi ki plus yi minus phi, as these two ki's are going to cancel. You notice this expression looks very similar to what we got up above here. So we can also split this out and solve for y, which will give us that yi equals ki zi over phi ki plus 1 minus phi. You'll notice this is the exact same denominator as this equation here. And we know that when we add up all of the vapor compositions, liquid compositions, they add up to 1. So knowing this, what Rashford and Rice decided to do is that they were going to essentially subtract our vapor mole fraction by our liquid mole fraction, which would give us sigma xi minus summation yi equals 0, as 1 minus 1 is 0. And then subbing in our big equations for this, we get the summation zi over ki phi plus 1 minus phi minus summation of ki zi over ki phi plus 1 minus phi. When we subtract these out, we get a combined expression the summation of zi times 1 minus ki over ki phi plus 1 minus phi equals 0. And this right here is our Rashford-Rice equation. And as you can see, it only depends upon known values from any given problem. Our feed composition for component I, our Ki, and then our phi, which is our vapor mole fraction, meaning that the Rashford-Rice is a monotonic function of only the vapor mole fraction. This is always either increasing or decreasing. So now, we'll go ahead and move into Python and see how this looks coded up. All right, one quick correction here. Here I subtracted our xi by our yi. I should have done the opposite and subtracted yi by xi, but all this changes for our equation is that we have ki minus 1, not 1 minus k. So now we are good to go ahead and move into Python and code this up. All right, now moving on to the Python section of this video, we are going to go ahead and implement our Rashford-Rice equation that we found up on the board by doing a little bit of a flash calculation, based off of our benzene toluene mixture we've been working with in previous homeworks. So to do that, we first need to define our function. So you define our flash PT as a function of our Z, our feed composition for component I, our P, and our T, our pressure and our temperature. And getting started here, we need to define our bubble pressure and our dew pressure. So we're going to use these previous bits of code up here to calculate those at our Z and our certain temperature. So we're going to say that our bubble pressure, our BP, is going to equal our bubble P at our composition Z and our temperature that we provide. And then we're going to say that our dew pressure is going to equal dew P at our Z and our T. Now what we need to do next is we need to make sure that our function is going to spit out an error if we're not in the vapor liquid equilibrium range. We either have all vapor or we have all liquid. And to do that, we're going to say that if P is greater than our bubble P, we are going to say return all liquid. And then conversely, we're going to say if P is less than our dew pressure, we are going to return all vapor. All right, now moving on, we are going to need to make an initial guess for our phi, which is our value up there. That's our single unknown in our Ashford rice, and a really good estimate is going to be our bubble pressure minus our pressure divided by our bubble pressure minus our dew pressure. And that's because we're like, our pressure, like we were saying before, cannot be higher than our bubble pressure. We have all liquid, so we're essentially seeing like how far we are in that equilibrium. It's essentially giving us a guess of how much vapor we have, our vapor mole fraction, because we've got our how far along we are between the vapor and the liquid. So that'll give us a pretty good guess for phi. And then of course we need to find our K, which is going to equal P dot PVAP, vapor pressure at T, over P, because that's going to be our saturation vapor pressure over our total pressure, which is our Yi over Xi, which gives us our K. So moving on from here, we need our root finding function. So we're going to define a root finding function again as fruit, and we are trying to find our actual phi. And from this, we're just going to return our Rashford rice equation. So we're going to return, looking up at the board here, our Z times our K minus 1, all divided by, put this in parentheses, all divided by, looking up on the board here, that's going to be our K times our phi plus 1 minus phi. And since we said that this is equal to 0, our Ashford rice is equal to 0, we can use a root finder to find our value of phi given our inlet composition for I and our pressure and our temperature. So to do that, we're going to use our SciPy root finder, but to do that, we are going to need our f prime, like our derivative, to find it, because the method that we're going to use requires that we supply the derivative as well. So we're going to use Jack's NumPy to find the derivative of this function before we go ahead and find the root for phi. So let's go ahead and do that. So we are going to say that f root prime, our first derivative of our f root, is going to equal Jax.gradient of our f root. And so that we get this computed nice and quick using our GPUs, we're going to say that f root is going to equal Jax.jit of f root. So we can use those GPUs and compute this super fast. So moving on from this, now that we have our f root prime, we can go ahead and find our root for phi. So to do this, actually need to kick these up into our function. I kicked them down. Go ahead and move these. We are going to say that scipy.phi is going to equal scipy.optimize dot root scalar of our f root with our x naught equaling our phi guess. From above, we're going to use the Newton method. And we're going to say that our f prime is going to equal our f root prime dot root. All right, so now that we have our root, we need to spit out our x and y as well. So we know that our x is going to equal z over 1 plus phi times k minus 1. From our equation up there on the board. Then we know our y is just going to be k times rx. And then we are going to have this big function spit out our phi, our x, and our y. And that should be our function for our Rashford rice. All right, now that we have our function here, you can shift enter. Oh, forgot to put a colon in there. Shift enter. Fantastic. We can go ahead and solve our problem. So we're looking to apply our function to a feed comprised of 40/60 moles of benzene/toluene at 1 bar and 370 Kelvin. So to do that, we're going to say flash pt we're going to say flash pt at numpy.array 0.6, 0.4, 0.6. We know that our pressure is going to be 1 E5 pascals or 1 bar, and our temperature is going to be 370 Kelvin. So let's see what this spits out for us. I need to put these in brackets. All right, what's up now? All right, so I found my problem. I need to take the sum of this, as we talked about up on the board. It's pretty important. So Jax numpy dot sum of all of this, and that should hopefully fix our error. And it did. Look at that. So it found our phi value. It found our composition of benzene and toluene in the liquid phase and in the vapor phase. And I believe that should be the end of homework 2 part A. We found our phi, and we have found the vapor liquid equilibrium behavior for our benzene and toluene mixture using our function based off of our Rashford-Rice equation up on the board. So I'll see you next time in part B.